How attractive is an organization to a hacker? How do you measure hackability across different organizations? 6 steps to reach from this unordered collection of issues to something much more focused where you can compare yourself to others. Hi, this is Carsten from Hacking Matters, where each week we discuss best practices in cybersecurity. Today, we look at how to compare yourself to others in terms of hacking resilience. How do you measure and compare what we call hackability across different organizations? It's a deep dive to a topic we discussed a couple of weeks ago when we talked about security metrics. I gave the example that counting vulnerabilities is not a good metric, but that we need something more to model how the hackers are thinking. And based on your popular demand today, I'm going to provide a little bit more deep dive on how we model this in what we call Hackability Score. Now, obviously, this is just an example. Your mileage will vary, but if you're looking for one possible way to measure hackability, this is going to be it. The Hackability Score is a technical metric that we use to answer one question: how attractive is an organization to a hacker? And this is one of the few places in life where you want to be as unattractive as possible. You want the hacker to look at your technology and say, not much to leverage here. I'd rather hack somewhere else that looks more promising. Before implementing a metric like the Hackability Score, your situation will look something like this. You have a bunch of different lists of issues, and you have multiple departments that are supposed to do something, programmers, admins, and somehow you as the security professional are supposed to bring that together. Look at all of these different lists, from vulnerability scanners, pentests, threat intelligence, what have you, and now tell the people who can do something about it, programmers and admins predominantly, what actions you require from them. So you're doing a translation job, but never does it feel like you're making much progress, because for every 3 issues you solve somewhere, at least 3 new issues pop up. And with more visibility, more scanners, more cloud environments and whatnot, it feels more, for every 1 issue you solve, 10 more pop up. So how do we know how good we are? And how do we create a sense of progression so that we know we're moving in the right direction? And that's exactly when you start implementing a metric like the Hackability Score. So I'll walk you through 6 steps to basically reach from this unordered collection of issues to something much more focused where you can compare yourself over time, so knowing that you make progress, but you can also compare yourself to others, knowing where you stand within a peer group. And I'll give you some technical details as well and show you the formula that the Hackability Score is actually computed with. I'll show you how this formula is built step by step. It's growing in complexity, of course, as we account for different factors, but hopefully you will be able to follow along as we're explaining each step in sequence. So the first step, even before diving into a formula, is to put everything into one list and to deduplicate and aggregate. What do I mean by this? Different issue sources, for instance, vulnerability scanners, have very different granularities, and different scanners could report the same thing under different names. So for you, the first step is to put everything into what we call issue groups. So one issue group could be, for instance, there's a Windows server and it's missing patches. That's all you need to know. Now, different tools will have different names for it. Some of them are calling for the Windows patch number. Some of them are listing a CVE, maybe alongside a CVSS score. Everyone has a slightly different perspective on the group that really is. That server is missing patches, and Microsoft provides all of these patches, and it's probably easiest to just install all of them in bulk. So you define these groups and you put all of your individual issues from all the different sources into these groups. We've been doing this for a few years for literally millions of different IT assets, and we came back with about 1,000 different groups. So there's really only about 1,000 different things you could possibly do wrong in IT that would lead to security issues. There's, of course, all the different patching things. There's different hardening areas. There's a few things around network segregation. There's a few things around identity management, but it is a finite space, and there's no organization that has all 1,000. So no matter how many vulnerabilities you have, and many of you will start from this from millions, it will shrink down to at most a few hundred of these groups that basically cover the entire ecosystem. As you're moving issues into these groups, you're also starting to normalize between different issue sources for granularity. Imagine one issue source saying the server's unpatched and another issue source listing every single exploit that would be possible. Now, in terms of number of issues, the second source would suggest a higher urgency, but really they're talking about the same thing. So as you're aggregating in groups, you normalize across these different issue sources. That's your first step, collecting issues in these issue groups. Step 2, assign a severity per issue group and per asset, for instance, per server. Looking at this Windows server from earlier, you have all of these missing patches. You ask the question, which is the highest critical one? We define 4 severities, critical, high, medium, low, and only the most severe one should matter. Everything else kind of stands in the shadow of the most severe one. So in each group, there's a dominant criticality being the highest one. Now, this does sound easy. However, don't forget that you might need to change the severity compared to what your raw data says. Different tools, again, have different ways of ranking severity. Some of them have 5 levels, some of them have 4, like we use it, but most of them have a tendency to inflate issues. As a scanner specifically, the purchase decision is often tied to how much you report on which severity. So if you report at the right severity and somebody else inflates that a little bit, they are bought more. So over time, it gravitates towards more and more inflation. So you need to set your own standard basically and maybe deflate where necessary, reevaluate. We set the 4 levels as the critical level is an immediately exploitable issue. Might not work 100% of the time, but usually if you show this issue to a red teamer, they know how to break into the technology asset. Second severity, the high level, is an exploit fragment, something that, depending on circumstances, is exploitable, but something else needs to happen, generally speaking. A high issue by itself does not give you access to the technology asset. The medium severity is an issue that helps with the hacking journey, often by way of disclosing information that is useful in exploiting and leveraging other issues, but isn't by itself exploitable. And then everything else is slow, and we don't even account that in the hackability score. So it's really those exploits, exploit fragments, and useful accomplices to an exploit that matter for us. Now, you can see how that somehow relates to CVSS. However, we find that even with CVSS scores, something can be hard to exploit even if it has a very high CVSS, and your red teamer will know the difference. Just ask them. You don't have that many possible candidates for critical and high issues, so run them by your red team, by your security consultant. They can quickly help you reevaluate those issues. Now you need to assign, in that second step still, a numeric value how these issues differ. We say it takes about 3 high issues to be as severe as 1 critical issue. Basically, if 3 of these exploit fragments come together, that usually makes for a full exploit because they can be combined in different ways. We also say that it takes 5 of the accomplices to make up for 1 of the high issues, or 15 of them to make up for 1 critical issue. So a lot of information leakage would have to come together to reach the same severity as 1 critical issue. So put all of these together, we basically assign a negative value of 15 to a critical issue, 5 to a high issue, and 1 to a medium issue. 0 to everything else. As we said, we disregard that, as do the hackers. And these numbers, 15, 5, 1, we call the hacking impact. So now for each issue group and for each server, you have the hacking impact. It's basically a big matrix, but of course most fields in that matrix are empty. almost all the issues are not present on almost all the servers. So it's kind of rare that an issue occurs. But when it does, you assign these 15, 5, or 1 negative points to the issue group. That was step number 2. Now we know the hacking impact of these different groups. To reach the overall hacking impact, we just sum over all the issue groups and over all the servers or other technology assets. So it's a simple sum over all the hacking impact. Looks simple enough. However, purely linearly summing up distorts the picture a little bit. Imagine you have a server with a certain set of issues. The server next to it has the same issues. The server next to it has the same issues. Now, having 3 servers with the same issues doesn't make your organization 3 times as attractive to the hacker. If they break in, they break in, and it probably doesn't really matter which of the 3 servers they hit. So we need to discount for this, basically saying if the same issue is present on multiple servers, it faces diminishing returns. And we account for this using the number of occurrences of this issue type, the issue group, across different servers. And we use the square root. The square root nicely models diminishing returns. It grows indefinitely, but of course slower and slower and slower as the number of occurrences keeps growing. So now we have a formula to have the hacking impact for your entire organization already discounting for the same issue being present on multiple instances and facing this diminishing returns. Next, we want to compensate for one other dynamic, and that is a visibility gap. Basically, different types of scan strategies give you different visibility. And just because you're using a more visible scanning strategy doesn't mean that your hackability is higher. Your technology is still the same. You just know more about this technology. And one good example is if you use a standard scanner like Qualys or Nessus or Rapid7, they usually offer 2 modes. You scan over the network, basically scratching the surface, or you run an agent on the server itself, giving you many more data points, but basically describing ultimately the same hacking surface. We call this difference the data source expressiveness, DSE in the formula. Basically saying, in this example, switching from a network-based scanning to an agent-based scanning, you would expect maybe 10 times as many issues. So a single issue discovered over the network is as likely as 10 issues discovered with the agent-based scanning. But we need to account for this in our formula. We basically need to say, where does this information come from and what was the data source expressiveness, so that if we do combine different issue sources, that they're fairly merged rather than giving an overweighted influence on the agent-based scanning, for instance, compared to the network-based scanning, or compared to your pentest, or compared to your bug bounty. All of those are relatively infrequent but high signal sources, whereas the agent one is a much more frequent, therefore lower signal source, if that makes sense. Now we have a formula that sums the hacking impact over all your assets, over all your issue groups, but acknowledges that it matters where the information came from. And after these steps, we've already reached what we call hackability in its first variant, the absolute hackability. Basically, you know the overall hacking risk based on the data sources that you put in here. So that's the absolute hackability score. Let's look at a concrete example how to compute it. Imagine you have a network with 8 computers, and you scan that with a relatively simple network-based scanner, something along the lines of Nessus or Qualys. You get a report back that says we detected 2 different types of vulnerabilities. One vulnerability type is present on 4 of your computers. The second vulnerability type is present on 1 of those 4. So you have 5 vulnerability instances total, 4 of one kind, and we say this is a medium severity vulnerability as per our earlier definition. And the 5th vulnerability is of high severity. So that then translates into the hacking impact points. Each medium severity maps to 1 kind of negative hacking impact, and a high severity one maps to 5 negative hacking impact points. In summing over these individual hacking impacts, we now have to account for the different factors. The first factor we said we want to account for is diminishing returns if a vulnerability is present more than once. So this first vulnerability type is present 4 times. We said we want to divide by the square root of the number of instances. So in this case, square root of 4 or divided by 2. So the 1 hackability point becomes half a hackability point. Whereas the 5 points of the high severity, they remain because there's only 1 instance. So you basically divide by the square root of 1, which is 1. The next thing we want to account for is the data source expressiveness. In this case, we choose a 2, basically saying the network-based scan doesn't have very much information. Otherwise, this number would be significantly higher. But it's better than, let's say, just an Nmap-based scan with a few scripts switched on. That would be a DSE of 1, for instance. So normalized by this Nmap scan, Qualys is about twice as expressive. So you divide by another 2. So the original 1 became half because of the number of instances and becomes a quarter now. The 5 became 2.5, plus the quarter that's also present on the other 3 computers. You sum all of this up, and you have an absolute hackability for this scope of 3.5. Absolute hackability is useful for measuring progress over time. If you keep testing the same assets and the hackability score changes, that means those assets became more or less hackable in their time frame. Comparing over time, however, is not everything we want to do. We also want to be able to compare different companies. And you might have already noticed the absolute hackability is typically larger for large organizations and smaller for smaller organizations. So the more assets you have, the more the sum will accumulate different vulnerabilities. So we need some way of now size adjusting this, making sure that organizations of different size can be compared, or even parts of organizations. Maybe you want to compare your Windows environment to your Linux environment, but you have many more of one server type than the other. Comparing between them needs now what we call the normalized hackability score. So there are 2 more steps to go from the absolute hackability to the normalized hackability. The first is we need to adjust for the size of the organization, and we define size as the number of reachable TCP ports, basically saying it's a proxy for the amount of technology you have, how many TCP ports are reachable over your network. Again, you could use different heuristics, but choose one that you think represents the size of an organization. Now, we could simply divide by that number, basically saying if you have twice as many technology assets, it's okay to have twice as many vulnerabilities between them. But for me, this doesn't really account for the dynamics, because if you do have twice as many servers, there's more opportunities that hackers pick up different fragments and puzzle them together into an exploit. So basically, the more data you give the hacker to play with, the more the chances that they can craft an exploit from what they're seeing. So the diminishing factor here must be growing slower than the size of organization, basically demanding of larger organizations to be better on average in terms of vulnerabilities per asset compared to smaller organizations to reach the same hackability because of those effects where hackers can puzzle together from different sources. Once again, we want to model basically the diminishing returns here. And once again, we use a square root factor, this time over the number of TCP services. That leaves just one last step. And this last one is mostly optical and for that reason optional, but you might have noticed that the hackability score can grow indefinitely if you have more and more vulnerabilities. To the human mind, in my experience, it's easier to think in terms of a scale. And for the hackability score, I would like a scale between 0 and 100. So how do we now project a possibly infinite number on a scale from 0 to 100? We again need kind of a diminishing returns formula, but one that has a clearly defined n. Of course, we can just use an exponential function here. The normal exponential form is the one that in our experiments modeled the best what we're trying to express. So basically, you say that all hackability scores that could possibly exist are projected onto this scale between 0 and 100. And from the experiments that we have run, all values do kind of exist and roughly equally likely. So if you are around the 50% mark, then there is about half of the organizations in the world that are less or better secured than you, and same for all the other data points. Very roughly first approximation. And there you have it, a closed form formula to go basically from an unordered list of issues from all kinds of different sources, scanning, pen testing, threat intelligence, what have you, to a single number that, for whatever scope you choose, gives you the hackability and allows you to compare it to any other scope that you choose, inside or outside of your organization, assuming, of course, you have those same input lists of data. Coming back to our numbers-driven toy example from earlier, you remember the 8 servers with a total of 5 vulnerabilities across 4 of these servers? The absolute hackability for this scope was 3.5, which now we want to normalize in 2 steps. First, we normalize by the size of this scan scope. We have a total of 8 IP addresses, each of them exposing 2 TCP services. So the size expressed in TCP services is 16. So we divide again by the square root of 16 for these diminishing returns. That's 0.875, but that's not the normalized hackability score yet, because the second step is to put that on the 0 to 100 scale. And in this case, we derive a 58. This is slightly worse than average if you say your average is this 50 line in the middle. Now do note that most of this hackability comes from the one high severity issue. So if you fix that issue and leave all the medium findings alone, your normalized hackability drops to 38. So now you're significantly better than average. Small changes in your inputs can have significant impact on the hackability, but not all of them do. Imagine you remove one of the medium severity issues. Now you still have 3 left, so your diminishing return factor goes a little bit down. Instead of square root by 4, divide by square root of 3. These were small values to start with, so the hackability drop is almost irrelevant if you just fix one of these. If you fix all 4 of them, your impact will be significantly greater, because now you eradicated the root problem. You didn't change on the margin, where anyway the hacker only looked at diminishing returns, but you removed the whole class of problems. So those are the types of decisions that the hackability score steers you towards. This discussion on hackability score neatly ties into some of the other topics we've discussed on the channel. For instance, security metrics, of course, this being one example, and an example that illustrates really well how you steer behavior by way of choosing the most important issues to influence your hackability score the most, and thereby encouraging people to fix those first if they want to have an outsized influence, doing little work to have a big impact. But it also ties in, of course, to our discussion on risk acceptances. Maybe you do accept a certain level of hackability depending on what risk class an application or a server park falls in, so that you don't have to always renegotiate before every launch which issues are acceptable and which not, as long as the overall envelope stays below a certain threshold. This was a little bit more technical video than usual. I hope at least some of you enjoyed this. Do let me know if you want the channel to go more and more into technical detail, or whether you prefer to stay a little bit more on the organizational level. I love speaking about both, so it's just a question of when, not whether we will get to both on the channel here. If you enjoyed this video, please show it with a like and subscribe, and follow for more updates. I'll talk to you next week, and until then, happy hacking.